Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my series of videos on partial differential equations. And in particular, the focus of this presentation is on a maximum principle for harmonic and subharmonic functions. So I'm going to state the maximum principle and I'm going to prove it. And in other videos we'll look at the applications of the maximum principle to partial differential equations and boundary value problems. Okay, so the following result is known as a maximum principle for subharmonic functions. Subharmonic functions because we have an inequality here rather than, say, an equality. If it was equality, we'd just have a harmonic function. Now this sort of delta type notation is just to signify the Laplacian operator. Sometimes it's this nabla squared. Essentially it's just you take the gradient of u and then you take the divergence. So let me just sort of write that out. So that's the gradient of u, that's the divergence of the gradient, and in sort of longhand it's something like this in the plane, where the partial derivatives the subscripts mean partial derivatives. Okay, so let D be a bounded and connected set, say lying in the xy plane, and let U be a function of two variables that is subharmonic in D. If U attains its maximum value m on D plus the boundary, that's what this closure, or the bar D means, at any point in D, then U is identically equal to that maximum value. In other words, U is a constant. All right, so if you think here, D is the interior, this is the boundary, and D bar is this, okay, then this result is known as a maximum principle. Okay, so we're going to prove it, and in other videos we'll apply the ideas to partial differential equations. So before I get to the proof, let me just show you what we did in a previous video. We looked at the first mean value theorem for harmonic functions and subharmonic functions. So suppose you have a harmonic function where you have equality here. In some open set, if we have some sort of disk or ball centered at AB with radius r, then the value of the harmonic function u at a point AB is equal to the average value of u over any circle. And if you sort of put an inequality here, so you introduce, say, a subharmonic function, then you can have an inequality in your conclusion as well. And in fact, this is what we're going to use in the proof of our maximum principle result, because we're using a subharmonic function. Now, if you weren't using a subharmonic functions, you had inequality here, you could just use this straight away. Okay. All right, so how do we do the proof? So we're going to, I guess, argue by contradiction. So let's let U attain its maximum value m on the closure of D at some point in the interior. And what we're going to do is assume that U is non-constant. Okay? Now, if we start with this inequality here, what do we have? So essentially you're replacing A and B with x naught and y naught here. Then it follows that this holds. Okay, this is equal to m, and from inequality 4 you get this, and then u, because this is the maximum value of u, this is always less than or equal to m. So you can basically put an inequality here, replace this with m, and then you're basically left with a constant which you can shift out the front. So you're basically taking a scalar line integral of 1, which is the length of the curve. And if it's a circle with radius little r, then basically you'll get 2 pi r. So you get m over 2 pi r times 2 pi r, and that's m. Okay, so what is important here? It means that this thing here, this average value, is less than or equal to m and greater than or equal to m. So what does it mean? It means that this average value is equal to m for all circles centered at x0, y0. So this can only occur if u is equal to m. Okay, because if you vary the ball, you would expect this to vary. Okay, but it's not. It's constant. So the only way that this can happen is if u is identically equal to m on every circle centered at this point and lying in D. Okay, so let's then start the sort of argument where we look for our contradiction. Let's assume this holds, but this doesn't hold. Okay, so there's some point lying in our set D such that u is not equal to m, and just for definiteness, let's assume it's less than m. Okay, so you've got some sort of, say, set D. You've got a point here, x0, y0, where u takes on its maximum value, and you've got some other point over here where u is less than the maximum value m. Okay, now we know that just from this argument up here, that if I draw any circle around this point here, I know that along each of these circles u is constant. I proved that over here. Okay, so along each of these circles u is constant, and in fact it's equal to big M. Okay, so let's draw a curve from these 2 points. Okay, now I can do that because the set's connected. All right. Now, because u is continuous and u is equal to big M here and less than m here, there must be some point along this curve where some sort of last or first point, depending on which way you're moving. So if you move from here to here, there'll be a last point where u is equal to m and it drops down below m. Okay, so let that first or last point, however way you look at it, be, I know it's a bit small, but be, say, this point here. Okay, now at that point, u is still equal to big M, the maximum value. So it has all the same properties as this point here. Okay, so if I draw another circle around that point, u is identically equal to big M on this circle. But hang on. After I go past this point here, say to the right on this curve, the value of u drops below m. And there's an intersection between the orange curve and this red circle. So on all the other points of, well, at least one other point of the circle, we're saying that u is a constant and equal to m, okay, at all the other points. But on the intersection of this circle and the orange curve, we know that u is less than m. So there's our contradiction, okay? So u not identically equal to m on any sufficiently small circle centered at this point. So that contradicts what we came up with over here. So this contradiction then proves the result. Okay, so that is a proof of a maximum principle. It's nice and geometric, if you like. And a couple of twists or generalization. Well, let's look at it another way. If D's bounded and connected, say D's like a ball or a disc or something like this, and use non-constant, you must take its maximum value on the boundary, because you're working with a compact set there, and a continuous function has to achieve its maximum somewhere. So if it's a non-constant function and it doesn't have attain its maximum value on the interior of that set, well, it's got to have its maximum value on the boundary. Okay, that's essentially what this is saying. Okay, and if here we're using subharmonic functions. If you flip the inequality around, then we call these superharmonic functions. Then you can come up with a sort of analog minimum principle. Okay, and what does this mean for, say, a harmonic function? Okay, when we talk about harmonic functions, we just mean we have equality. For a harmonic function, essentially what the maximum principle says is that the function u must attain its maximum and minimum values on the boundary of the set. Okay, so there are some variations of the maximum principle, and we're going to apply it to various boundary value problems for partial differential equations. So I hope you can join me for those presentations in the future.